Hello and welcome back to the next chapter of the KNX basic course, the KNX telegram. In this chapter we discuss the detailed structure of the KNX communication protocol, which is called KNX bus telegram as agreed. We also learn why KNX data transmission on twisted pair, that means the two-wire line, is particularly effective and secure. Transmission of a telegram general. In order to understand how data transmission in a distributed serial system takes place without synchronous clock, we imagine a discussion round with several equal participants. Such a round table requires that certain rules be observed. These are called 1. Each participant may speak as long as no one else is already talking. 2. The talk time is limited to a maximum talk time per statement. 3. If more than one participant starts speaking at the same time, a procedure must be determined for dealing with and resolving a speech collision. 4. There are basically two types of communication. The direct communication between two partners, which consists of a series of alternating statements, and the undirected communication in which the statements are addressed to all or a group of the other participants. Transferred to KNX looks like this. First assumption. A telegram has just been terminated with a short collective acknowledgement. A new event occurs. That means pressing a button to switch on a light source. The push button must first wait until the agreed waiting time, T1, between two telegrams has elapsed. Then he starts his transmission process. Assuming that it is now the only transmitter, the entire telegram is now transmitted on the bus line. It is received by all other participants of this line segment at the same time, even by the transmitter itself. In this period of time, all recipients check the telegram, whether it is logically okay and whether they were addressed in it. All addressed subscribers send a simple acknowledgement at the same time after T2 has elapsed to confirm that they have received the telegram. In the discussion group mentioned above for comparison, this would mean that the speaker asks the listeners to answer whether they have understood his statement. At the same time, the listeners respond with, "Yes, we have." The telegram structure. Let us now go into more detail and look at the contents of the telegram. We always speak of a so-called header and useful information. The header, often referred to as protocol frame, contains bus-specific information required for transmission from the transmitter to the receiver. The useful information contains the actual data required for a particular task. In addition, the structure also describes the architecture of the entire protocol information. In KNX, the data is transmitted character by character. Calculation of the time requirement. A single character in the KNX telegram initially consists of 8 data bits, or 1 byte. Because there is no synchronization clock, additional information must be sent within the character, which enables the clear distinction between the individual characters and their good recognition. This is at first the start bit and at the end the stop bit. On the other hand, a so-called parity bit is also sent, with the help of which the receiver can detect various transmission errors, bit errors. Finally, there is also a 2-bit long pause time, so that even if there are differences in the processor clock speed of the transmitter and receiver, it can be safely synchronized back to the next byte. The KNX bus operates at a transmission rate of 9600 bit per second. This means that one bit is exactly 104 microseconds long. A character consists of a total of 13 bits, thus it occupies the bus for 1.35 milliseconds. Let us now come to the total length of the telegram. The KNX bus standard specifies that standard telegrams may contain useful information between 1 and 16 characters, which means transmission time from 1.35 to 21.6 milliseconds. For the entire duration of a telegram, the header information and pause times must now also be taken into account. The header contains 7 characters. The acknowledgement 1, pause T2 is also 1 character long, while pause T1 is 2 bits shorter than 4 characters. This together makes 13 times 1.35 milliseconds minus 0.21 milliseconds equals 17.34 milliseconds. This results in the following time requirement. For the shortest telegram, information only 1 character. These are the telegrams for connection management, which is connection establishment or termination, 18.65 milliseconds. For the shortest normal telegram, information 2 characters with 1 bit switching, 20 milliseconds. For the longest telegram, 40.25 milliseconds, 16 characters information. Converted to telegrams per second, this results in maximum 50 telegrams per second, minimum 25 telegrams per second. Just remember this statement. A KNX telegram can take between 20 and 40 milliseconds. Telegram acknowledgement. Let us now take a look at some of the characters in detail. The acknowledgement character is shown here. There are 3 different acknowledgements as in normal life. Understood, receipt correct. Not understood, receipt incorrect. And busy, understood but not able to handle the message. When the latter 2 receipts are sent, the sender of the information must repeat. He can do that up to 3 times. If a non-positive acknowledgement still results after the 3rd repetition, the communication must nevertheless be terminated. Incidentally, there is also the case that no acknowledgement is received at all, either because the destination address does not exist at all, or because the telegram has actually been changed so much by interference that no one can consider it valid. In this case, the transmitter must also repeat up to 3 times. The effects of the special bit sequences of the 3 acknowledgement types are discussed later when we talk about collision detection. Numbering systems. This and the following 4 slides are intended only for a better understanding of the common numbering systems usually used for digital communication. While decimal numbers are also common in KNX applications, these numbers have to be converted internally into the dual numbering system. As we have seen, we can better understand the way how the KNX bus works only when looking at the single bits in the characters. For better readability, shorter columns of numbers, however, the hexadecimal numbering system is used in displays such as the group monitor. The person designing and operating a KNX system with ETS does not usually have to deal with it. However, it can still be helpful to take a closer look at it, as you can see the bus telegrams in the monitors of ETS always also in the raw hexadecimal format. Telegram data formats. In group telegrams, as we have learned, application-related, different data lengths are transmitted. These data lengths must also be formatted, especially if it is not only one bit. This means that they must correspond to the so-called data point types. You can see a selection of them in this table. We have already discussed common data point types in the chapter Communication or System Overview. Conversion of numbering systems. If you don't have a computer app that converts a hex, dual, and decimal number into each other, you have to use the conversion methods shown here. Two simple examples. Example 1. Converting a hex number into its decimal value. The number A9 hex must be split into its individual powers based to 16. So the result is 10 times 16 plus 9 times 1 equals 169. Example 2. Converting a decimal figure into its binary representation. The algorithm is quite easy. You must divide the original decimal number by 2 and write down the remainder beginning on the right side. Then you continue dividing the resulting figures by 2 and writing down the remainders to the left until the result becomes 0. Now the conversion is complete and you can see the binary value of the original decimal figure. KNX bit transmission. Before we turn to the individual meanings of the TP telegram characters, we want to learn how the transmission of individual bits takes place on the TP KNX medium. As you can see, there is only a current flow when sending a 0 bit. What is behind this is an electronic switch in the bus coupler transformer module that short circuits the bus for approximately 35 microseconds. So the voltage initially collapses. When the switch is opened, it rises again by twice the value by which it broke in. This happens due to the behavior of the chokes in the power supply unit and the bus coupling unit. The doubling of the original switching amplitude by the inductivities also improves the detection quality in the comparator of the receivers. Telegram collision handling. The fact that only the 0 represents active current flow ensures that you can see at any time whether other subscribers are still transmitting at the same time. That means whenever one of them is sending 0, while the other transmitter is not allowed to do anything because it has a logical 1 in the bit order at the same time. The 0 therefore overrides the 1. The subscriber with the 1 will notice this, because it also notices that the bus voltage is breaking down, although it itself does not send. This means that it must first postpone its transmission request and wait until the telegram of the other subscriber has been completely transmitted. It must even receive this telegram now, since it might be meant for it now. You can also compare this procedure, called CSMA CA, with the use of walkie-talkies. If you press the send button, you can speak but not hear, corresponds to sending a 0. If you release the key again, you can hear again but no longer transmit, corresponds to sending a 1. By the way, CSMA CA is the abbreviation for Carrier Sense Multiple Access with Collision Avoidance. In the picture above, you can see that in the 5th bit, subscriber 1 transmits a 0, while subscriber 2 has a 1. So subscriber 2 has to abort the transmission now. One more word on repetition. A telegram cancelled in this way is considered not to have been sent at all. This subscriber may attempt to send its telegram until it has sent it completely. only then it is considered to be sent for the first time, which is followed by an acknowledgement. If we now look at the acknowledgement frame again with the knowledge of collision detection, here we see that the two non-positive acknowledgements for bits D2, D3 or D6, D7 have 0 bits in each case compared to the positive acknowledgement. These override the 1 bits of the positive acknowledgement and assert themselves. The sender of the positive acknowledgement will terminate at that moment. Due to the different position of the zeros of NAC and busy, busy can also override the NAC frame. Now to another important character in the telegram, the control field. This is the first character of the telegram. If we compare it with a postal letter, information such as priority, registered letter, postage, etc. can be found here. For KNX standard telegrams, there are 5 fixed and 3 variable bits in this control field. Let's first look at the reading direction, which is also the time axis from right to left. The first 2 bits are fixed to 0. As the start bit always comes first in the character, each bus telegram always starts with 3 0 bits. With that, it has a special purpose. As already explained with the collision detection, only 0 bits are visible on the bus line. That means through an oscilloscope. 1 bits are passive. With 3 times 0 in succession, it is therefore very likely that a real KNX telegram will now start and not, for example, only an electromagnetic interference. This introduction of a telegram is therefore also called preamble. Already after the second 0, no other bus device can actually start transmitting. With the third 0, the bus is finally occupied. Only for telegrams sent in parallel, other rules now have to be applied. That means the rules of collision detection as described above. The next 2 bits for the transmission priority prove this. 4 priority levels can be distinguished with 2 bits. The highest level, system priority, only uses the ETS when programming or reading devices. The other 3 levels can be set by the user in each communication object. But beware, since there are only 3 options, you have to be economical with the allocation of higher priorities. Moreover, the priority only takes effect if 2 or more telegrams really start at the same time. The priority is followed by a 1, which is passive as we know, and then the repeat bit. In the case of a repeatedly transmitted telegram, it must be set to 0. The sense is clear. Repeat telegrams should go out as fast as possible. Therefore, their priority is increased with this bit. On the other hand, higher priority bits have priority over repetition. The sender address, also called source address, follows the control field, as we know the individual address of the sending subscriber. This is also extremely logical. It is again about possible collisions with telegrams sent in parallel. In the control field, there is still a high probability that a collision is present but not detected because the bit sequences are identical. Now, with the individual address, this can't happen anymore. As agreed, each individual address may only occur once. For this reason, there will be always at least 1 bit difference within the 2 characters for the sender address in case of colliding telegrams. Thus, it is decided from here at the latest who is allowed to continue sending and who has to wait. Destination address. Characters 4 and 5 represent the destination address. With information about the first 3 characters and about collision detection, it is now clear that only one transmitter can remain active from the target address onwards. While the source address can only represent an individual address, due to the uniqueness of the sender, the target address can of course be both group and individual address, depending on the purpose of the telegram. We have already learned about the structure of these addresses elsewhere. As a reminder, here again the 3 options of structuring for the group address. 3-stage with bit distribution 5/3/8. 2-stage with bit distribution 5/11, and 3 without defined structure. In the free structure, the planner can determine how the group addresses are to be structurized, and thus has the highest possible adaptability. How does the recipient distinguish whether the destination represents an individual or a group address? Now, since there is no way to do this within the 16-bit, it can only be coded after the address in the following character. On the picture you can see that the destination address contains 2 bytes plus 1 bit. This is the most significant bit of the next character, which also contains information about the routing counter, see next slide, and the length of the user data. If this discrimination bit has the value 0, the address is individual. Otherwise, that means if equal to 1, group. Routing counter. The routing counter has already been discussed in the topology chapter. Here you can see its arrangement in the telegram. The routing counter shows how often a telegram has already passed a coupler or router. Sometimes it is also called hop count. Telegram handling by the couplers and routers in context with the routing counter. Each coupler decreases the routing counter value by 1 and forwards the telegram as long as the result is not 0. And of course, the filler table is always taken into account if a group telegram is present. If target equals individual address, the coupler compares it with its own address and then decides whether the telegram may be forwarded in relation to the direction. Service value equals 7. If, for example, the routing counter with a value of 7 is sent by the service device, which in most cases is the PC with the ETS, the couplers do not change the value. The telegram then is transmitted without observing any filter options over the entire KNX bus system and thus reaches the desired subscribers regardless of the line in which they are installed. In the case of an erroneously cross-line loop, as shown here between the 2 second subline segments, the routing counter limits the number of circular telegrams, thus preventing a complete system standstill. Error detection and elimination. As experience has shown that this error occurs again and again, here are some hints for its detection and subsequent correction. First, the user notices that everything is running a little slower than usual. This is because each telegram passes through the loop in 2 directions and must therefore always be transmitted 12 times further until the counter is set to 0. The service technician then sees the same bus telegram in the bus monitor several times, but with different routing counters. For example, in the loop shown here at the place of the red cross and in case of transmission on this line, the values 6 when sending and 2 times the values 0 when receiving. On the basis of the pattern of these routing counters, it is usually possible to see where the loop was formed. At 6, 0 as shown here, For example, if a main line is connected to a subline, then the complete routing counter sequence 6, 5, 4, 3, 2, 1, 0 would be observed, and for each routing counter again 2 telegrams except for routing counter equals 6. In this situation, it is no longer possible to program or analyze bus subscribers, since the ETS reacts to identical response telegrams that have been sent repeatedly with connection termination. The search for the error can be complex. It is similar to the process of searching for an insulation fault after an RCD switch has tripped. First, switch off all bus power supplies. All choke reset switches must also be set to reset. This means that the bus is short-circuited on all segments. Now you start segment by segment to open the reset switches again and switch on the power supply. If it is on a normal operating indication, that means mostly green LEDs on, the segment is not affected by the loop. However, if a short circuit is signalized, all reset switches of the other segments that have not yet been checked are opened one after the other. As soon as the short circuit disappears, the corresponding segments are determined. In case of a simple looping, only one wrong connection, only the location of the wrong connector has to be found. But this alone can now be quite tedious again. With multiple loops, multiple connections, you proceed with the same logic, but you have to be aware that it will take much longer. For this reason, it should be clearly pointed out here that the installers who only do the cable laying should also be informed about the consequences of all too sloppy wiring. Useful data. Finally, the length information for the user data follows in the 6th character. It is the remaining 4 bits. This is used to encode how many characters will follow. This enables the receiver to detect and reject incorrect user data lengths. This length specification is comparable to a fax that uses a cover sheet. On the cover sheet, for example, is then written, "This fax contains 15 pages. If the recipient does not get exactly 15 pages, he has to check why. 4-bit length coding also means that a maximum of 16 characters can be transmitted. The counter naturally starts with the value 0, 4 binary zeros, which corresponds to 1 character of useful information, and ends at 15, corresponding to 16 characters. By explaining the data point types, we have learned that a group telegram can contain a maximum of 14 bytes of user data. So what happens to the other 2 bytes? This is control information. In the picture they are shown as XXXX and CCCC. For example, CCCC contains the commands value write, group telegram write, value read, group telegram read, value response, group telegram response, and memory write. XXXX also have meanings, but not for group telegrams. Check byte. The last byte in the telegram is the check field, also called check byte or checksum. Together with the parity bits of the individual characters, it ensures that Foley telegrams in which one or more bits are incorrect are reliably detected and rejected. A complementary algorithm is used, which enables the evaluating controller program to quickly and easily detect the errors. First, you have to know that the receiver of the data recalculates parities and checksum itself. It then compares its results with the values received. Even if there is only 1 bit difference, the telegram must be rejected. The algorithm looks like this. A cross sum of all bits is calculated over each byte. The parity bit has the value that must be added to achieve an even number of results. It is called even parity. With this measure alone, 99 out of 100 faulty telegrams can be detected and eliminated. But that is not sufficient. Therefore, also the length or odd parity is formed. Here 8 cross sums are calculated, albeit lengthwise, over the entire telegram, whose addition is transferred to an odd result in the check byte. In this case, the bits are added up in the same position. The error rate for this procedure is also 1%. That means 99 times good, 1 times bad. Taken together, however, the multiplication results from both probabilities, and that is already 1 per 10,000. This means that now only 1 out of 10,000 faulty telegrams will not be detected according to this procedure. This kind of error reduction, by the way, is called cross-parity check. However, since there are further content-related checks, for example, the user data length and the target group address check, it can be assumed that the probability that a faulty telegram leads to a normal switching action is 0. Symmetry in signal transmission. We know that the KNX bus must be routed floating. This has great advantages not only for electrical safety, but also for signal transmission. For this reason, other communication methods, such as Ethernet, have long since been using 2-wire buses instead of coaxial cables. Advantage in terms of the used bus cable, which is shielded and twisted. Interference radiation from outside, if it is not already blocked by the screen, strikes both cores of the KNX quite evenly. As a result, the potential of both cores shifts by the same amount. In bus telegram transmissions, however, the difference between the 2 wires is important, and this always remains the same. Thus, interference signals have hardly any negative influence on the transmission quality in the KNX twisted pair system. Effect of the choke in the power supply unit. The KNX bus cable serves 2 different purposes. On the one hand, it is the carrier for the communication signals, the bus telegrams. These represent an alternating voltage. On the other hand, the bus coupling controllers of the bus nodes should also be supplied with the necessary operating power via the same line. That's a DC voltage. For this reason, the bus power supply initially produces a highly constant DC voltage with very low residual ripple after rectification. If the bus telegrams were simply fed into the power supply connection, they would be immediately short-circuited by the stabilizer circuit. Therefore, a choke is now used between the power supply unit and the bus. A choke is a coil and thus represents an inductance. The inductance has no effect on direct current. Here only the winding resistance of the choke is decisive, and it's very small. For the AC voltage, however, the inductive resistance of the choke, the impedance applies. It is proportional to the frequency of the AC voltage. The power supply can therefore no longer short-circuit the telegrams. Logically, the reverse must then happen for the bus devices. There, the AC and DC voltages must again be separated with the aid of suitable electronics. Cable lengths. Already in the chapter installation, the cable lengths were mentioned, which must not be exceeded within a line segment. Here are the explanation of how this information is obtained. Distance between power supply and subscriber. The loop resistance is responsible for this. The bus line has a loop resistance of approximately 73 ohms per kilometer. A maximum of 25 ohms is permissible so that the bus voltage does not fall below the minimum voltage of 21 volt within a maximum load at the end of the bus line. Distance between two participants is the double as the distance subscriber power supply unit. On the one hand, this seems logical because you don't have to think about it if you pull two stub lines, which must be longer or shorter. But on the other hand, it is also due to the technical reasons in connection with the maximum permissible cable length. This is about the runtime of the data transfer. It is determined by the cable capacity. It is only 120 picofarad per kilometer, but in combination with all other factors, it leads to the fact that beyond the 700 meter distance, the collision avoidance does not work anymore. The total cable length in the segment is determined by the maximum permissible cable capacitance. Theoretical and real signals. The signal form of the bus telegrams looks quite unusual and has little in common with the original rectangular digital bit sequence. The original unadapted square wave signal could not be transmitted on a twisted pair line. The upper graph shows how the signal should look ideally. First comes an active zero pulse, followed by the inductive response pulse. At the end of the bit period duration, the reference level, that means the bus voltage, must be reached again, so that the next bit pulse, if zero, starts again at the same level. This is important because no matter which bit sequence is transmitted, there must never be a reference point shift. Otherwise, the receive comparator in the bus coupler would no longer be able to operate reliably. This is achieved by the duty cycle between the active and the remaining period duration. It is about 2 per 1. In other words, the active impulse is about 35 microseconds long, followed by 69 microseconds response impulse. The picture below shows the real signal path of an individual bus node without any further loads. The amplitudes are about minus to plus 7 volts. You can see that the return to the zero line does not work properly, but the next impulse still reaches the negative amplitude drop exactly as before, so the procedure works as desired. Maximum line load. This oscillography shows the worst case, which is present when a line segment is occupied by 64 subscribers at rated current of the power supply, and the two bus couplers furthest apart have 700 meter bus line between them. Above you can see the signal at the sender's location. The maximum transmission amplitude reaches only approximately minus 3 volt from the reference level, the bus voltage. After 700 meters, it has dropped to only minus 1 volt because of the lead resistance. In addition, a propagation delay of approximately 10 microseconds has occurred, exactly the limit value up to which collisions can still be resolved. With this slide, you have reached the end of the chapter telegrams. Congratulations once more. Now, there is only one more theory chapter left to complete the basic course. So see you back in the last chapter, coupling of lines.